X-rays are used for surging bone fractures, but can also be used for analyzing any other matter. X-ray absorption spectroscopy, XAS, is an advanced technique used for probing the local environment of matter at atomic level, including its electronic structure. More specifically, by analyzing the absorption, the structure of it, and the position of the atoms in the structure can be revealed. Apparently, those X-rays penetrate matter, and an absorption spectrum of the various X-ray energies can be recorded. The frequency of X-rays ranges from 10 to the 16th to 10 to the 19th Hz. Due to this frequency range, X-rays are able to be absorbed by specific energy levels in matter. X-rays for analyzing bone fractures or other irregularities in living matter uses typically only one frequency, but we would like to see an absorption spectrum, meaning the absorption at specific frequency. To give intense and tunable X-ray beams, usually a synchrotron is required. Here fast traveling electrons are bent by magnetic fields to keep them in a ring. These electrons collide with certain matter to generate the X-rays. These X-rays are leaving the ring to be used in the desired experiment. The place where the tools are for doing the experiments is called a hutch. X-ray absorption spectra of any matter are characterized by a sharp increase in absorption at specific X-ray photon energies. This sharp increase is characteristic of the absorbing atom. This sudden increase in absorption is called the absorption edge. This energy at the absorption edge corresponds to the energy required to eject a core electron into the lowest unoccupied orbital, or to vacuum. The sharp rise, therefore, depends on the binding energy of the core electron in that shell, such as the K, L, M shell. K edge X-ray absorption corresponds to the excitation of an 1s electron, and the energy related to this absorption is typically in the order of 100 to 100,000 electron volts. In this example, we used a spinel lithium manganese oxide, LiMn2O4. Here the average oxidation state of the manganese is 3.5. One manganese is 4+, and the other one is 3+. We delithiated this spinel with a strong acid to form Mn2O4. Here the oxidation state of the manganese is 4+. For both materials we measured the X-ray absorption spectrum, and we see a clear shift in the edge. Now we expose the Mn2O4 material to a 1 atmosphere hydrogen by flowing hydrogen gas through the cell of the sample. This results in uptaking of hydrogen, similar as was occurring of lithium in a lithium-ion battery. The consequence is that the oxidation state of the manganese will drop to lower value. This gentle shift is also visible. Obviously, this method is interesting to monitor changes in oxidation states during operation. This is very often done for all kinds of battery materials. Not only the edge will provide information on the material, also the small peaks just before the edge. This region is called the pre-edge. Remember that the dominant contribution to the K-edge spectrum comes from 1s to the p transitions. For transition metals with partially occupied d orbitals, additional insights can be gained by examination of pre-edge features that results from 1s to various d transitions. These are relatively weak in intensity, but they can be detected as they occur at energy slightly less than that of the absorption edge. The pre-edge peaks provide information on the electronic environment of the atom. In X-ray absorption, the absorbed X-ray ejects a core electron, referred to as the photoelectron, from the absorbing atom, leaving behind a core hole. The ejected photon electron's energy will be equal to that of the absorbed photon minus its initial binding energy. The atom is now excited and the ejected photoelectron interacts with electrons in the surrounding non-excited atoms. The ejected photoelectron is assumed to act as a wave with the other atoms described as point scatters. The backscattered electron waves interfere with the forward propagating waves. The resulting interference pattern can be described with the Bragg relation. That means we will find constructive and destructive interference. The main difference with this interference is that this structure doesn't need to have long-range order. The effect of the backscattered photoelectron on the absorbed spectra is found in the X-Selfs region. The X-Selfs region therefore provides information on the atomic surroundings of the ion we are measuring. In summary, with X-ray absorption spectroscopy, we can analyze the oxidation state of the atom or ion in the Xanes region. In the pre-edge region, we can analyze the electronic structure of the atom or ion. In the X-Selfs region, we can analyze the atomic environment, the number of the surrounding atoms, and calculate the distance between them.